First of all, let us consider the factors which affect the propagation of radio waves. These factors fall into two categories, namely attenuation, which is the weakening of the wave, and refraction, which is the bending of the wave. Attenuation occurs in several ways. As the wave travels further away from the transmitter, it simply becomes weaker, like the waves in a pond emanating from where a stone is thrown. As range increases, the field strength of the wave decreases. It can be shown that this attenuation is proportional to the inverse square of the range. This means that if the range of the transmitter is to be doubled, the power required must be quadrupled. Surface attenuation occurs when a wave travels over the Earth's surface. Its strength will be attenuated by contact with the Earth's surface, because the wave induces a voltage in the Earth which takes energy away from the wave as it moves away from the transmitter. To reduce this attenuation, vertically polarized electric fields are used, which merely dip into and out of the Earth's surface, whereas a horizontally polarized field is in constant contact with the surface of the Earth, and the wave is completely attenuated within a short distance. The nature of the surface of the Earth over which the wave travels is also a factor in attenuation. Radio waves attenuate more over land than over the sea. Mountains, forests, and deserts cause the greatest attenuation of radio waves. Surface attenuation increases as the frequency of the signal increases, and so frequencies above 2 MHz are of little use for long-distance transmissions. Ionospheric attenuation occurs when radio waves penetrate the ionosphere, which is suffused with free electrons. As radio signals propagate through the layers of the ionosphere, they begin to transfer energy to these electrons, setting them in motion. This results in the electrons vibrating, which can cause them to collide with other molecules, ions, and electrons. Each collision dissipates a small amount of radio signal strength as energy is transferred from wave to particle, and the radio wave returning to Earth will have lost some of its strength. The frequency, and hence the wavelength of the radio wave, is important. The longer the wavelength, the greater the ionospheric attenuation. Note that this is the reverse of ground attenuation. Another type of signal weakening is atmospheric attenuation, or scatter. Because the atmosphere contains solid particles, such as water, pollutants, and ice, these will reflect and scatter radio waves of a sufficiently high frequency, those above 5 GHz. You will recall that the wavelength of radio waves in the 2 GHz bands, 3 to 300 GHz, ranges from 10 centimeters down to a millimeter. Water droplets have similar sizes, and that is why they reflect and scatter radio waves. Reflection of signals off buildings and hills, etc., will weaken any signal. Consequently, aerials should be positioned as high as possible or well clear of buildings and other causes of refraction. Static interference in the atmosphere also attenuates radio signals. It is caused by an imbalance of positive and negative electrical charges in atoms which come into contact with each other, causing electrons to be transferred from one atom to another. Rain and thunderstorms and solar activity are the frequent cause of static interference, and it is worse at lower frequencies. If there is much static interference, the strength of the signal may have to be increased. The strength of the signal compared to the amount of interference, measured in decibels, is known as the signal-to-noise ratio. If internal noise in a receiver can be reduced, then the receiver will be able to process weaker signals, thereby increasing the effective range at which a usable signal can be received.